Welcome to the next video on mathematical statistics. This is video 3 on a few useful probability identities. It corresponds to part 1, chapter 1, section 3 of the textbook. So here are the identities. The first one is that if you have a subset of B, then the probability of A should be less than or equal to the probability of B. I think this makes somewhat like maybe graphical or even other kinds of intuitive sense. But just imagine that you have, A a subset of B as depicted here, right? So, you wouldn't draw the Venn diagram this way because this would suggest, right, if A is over here and B is over here, it would suggest that some portion of A might be outside of B. But that's not what we're dealing with, right? We're dealing with this picture where A is the smaller set. And so it just kind of seems like it makes sense that like this visually smaller set should have a smaller probability. And we'll prove it rigorously. Okay, this is the complement law, that the probability of any complement, by the way, I'm writing A to the C, that's our notation for the complement. There are various notations for complements. I actually can't off the top of my head recall what it is for the textbook, but these are all sort of various notations for the complement. So you'll see each of these in different textbooks. But I just basically all of them mean that I'm taking the entire sample space and removing the set A, right? So whenever talking about the complement, you always have to have a concept of like the universal set. And for us, that's going to be the sample space, right? The sample space is going to be the universal set. And so the complement is just taking the universal set and removing A, right? So it's everything other than A from the universal set, or for us, sample space. Anyway, it has this formula that the probability of the complement is equal to 1 minus the probability of the event. Then we have the probability of the empty set is always 0. The probability of any event is less than or equal to 1. And then if, again, returning to if A is a subset of B, then the probability of B minus A is the probability of B minus the probability of A. By the way, I should probably remark that this has a name, and since I will often call it by its name, I should tell you what that is now. This is often called excision. I believe I've spelled that right, although I could have it wrong, but it's called excision, and it's basically the idea that, if you do the probability of the set minus, then you get probability of B minus probability of A. A fairly intuitive result, but keep in mind that A being a subset of B is an essential feature of this, right? It would not work if you did not have A subset of B. Okay, we're going to move on to the proofs of these theorems. So here's the first proof. We're going to assume that A is a subset of B, and we would like to show that the probability of B is greater than or equal to the probability of A. So that's the big high-level picture of what we're trying to do here. As usual, when we're working so close to the axioms, we would like to cut our sets into disjoint components. We've already seen before that this is a natural way to cut our set B into disjoint components. In particular, because A is a subset of B, then, we would like to decompose B into two parts, right? The part that is A, and then the part that is outside of A, but still inside of B. So that's B minus A. So this is a way of cutting B into two disjoint pieces. We replace B with this carving. We then apply sort of additivity or distributivity, whatever you want to call that move, but there you have it. And now, let's notice that what we have at this point is, well, for one thing, equal to the probability of B. It has as part of it the probability of A, but then it also has this other part over here. Now, this other part right here is, importantly, greater than or equal to 0, because all probabilities are greater than or equal to 0. So Since we have a quantity here which is non-negative, then if I remove it, right, if I take away that positive or at least non-negative part, then I get something smaller, right? So this might seem like kind of tricky reasoning. A little bit it is, but it's totally valid. And so I get this inequality, right? So I get this inequality that the probability of A is less than or equal to this thing. But keep in mind that these things were all determined to be equal. So effectively what we've shown is what we wanted to show all along, right? That probability of B is greater than or equal to the probability of A. Now, I just want to emphasize the style of writing equations here. This may be completely familiar to the viewer, but I just want to sort of emphasize. Often when we're doing proofs, we're going to write down these sorts of chains of equalities and inequalities. And the idea is like, right, if I write that P of B, right, if I write that this is equal to this, we all know what that means. And then I write equal to this, right, with no kind of apparent left-hand side. What I implicitly mean is that everything here, all three of these, are each equal to each other, right? Which is, right, like, I mean, after all, this should make total logical sense, right? These two are equal to each other. These two are equal to each other. Well, it then follows that these two are equal to each other. So, the point is when you get these like chains of equations, you just know that everything in the chain is equal to everything else in the chain. So that this is basically just three different ways of writing down the same thing. Now, sometimes in the chain you'll get an inequality, and all I'm saying there is that, any way that you pick any one of these things, because they're all the same thing, I am now sort of inferring that this thing down here is less than or equal to any one of these things up here, right? So that's kind of a standard style of working with equations and inequalities in these sort of proof contexts. So, okay, let's move along. So the next one was we were going to prove the complement law. And, so if we're trying to relate A and A complement, you kind of think that, well, omega is basically partitioned by A and A complement somehow, right? And so if the entire space is partitioned by these two things, it would kind of make sense that we would write down the probability of the entire space. Because after all, we know that the probability of the entire space, as one of our axioms, is equal to 1. So we have the justification that these two things are equal to each other. But also we can use axiom 3, first of all, we're just going to write down omega as its decomposition into the disjoint union of A with A complement. And then we can apply axiom 3, which is the countable additivity axiom. And so we just kind of add together each of the individual probabilities. And there you have it, right? We have now that all of these things are all equal to each other. And from that, it follows that if I, especially, right, like let's focus on the last two pieces, right? Those two pieces, if I take this and subtract PA to the other side so that I get minus PA, then this is the resulting equation that we obtain from that. And so that's the proof of the complement law. Okay, let's move on to finding the probability of the empty set. Now, the empty set is kind of a tricky object, and one nice trick with it is, well, it is equal to the union with itself, right? And in particular, it's a disjoint union, right? The empty set is disjoint with the empty set, simply because if you take their intersection, you get the empty set, right? This is all kind of trivial, although necessary to check. But in any case, right, so this is a completely valid equation. The empty set is equal to the disjoint union of the empty set with the empty set, right, this thing right here. And then because it's a disjoint union, I am free to use countable additivity and split up the probability so that now I get probability empty set equals probability empty set plus probability of empty set. Now, from here, I could subtract the probability of the empty set on both sides, right? If I subtract it, I'll cancel this one out and I'll cancel this one out, leaving on this side a 0 and leaving on this side just the probability of the empty set. And so it gives us this equation. By the way, again, on the note of how we typically write equations and stuff like that, here I've got a chain of equations. Once I make a move, right, because this is just like a new equation. It comes from the previous equation, right? I am making an inference from the previous equation, but I couldn't write this in line with the previous stuff. It's not equal to the previous stuff. So often I'll go through these sorts of long chains of equations and sometimes inequalities, but every now and then, to get to what I'm trying to actually arrive at, I need to, stop my equation and make some inference from the equation. Often that's like subtracting something from both sides or multiplying something on both sides or whatever, right? Those standard algebra moves, that's going from one equation and inferring a new equation. And that's what's going on here, right? So from this system of equations, I infer this equation by subtracting the probability of the empty set from both sides. Okay. Let's move on. So if A is any event and we want to prove that its probability is less than or equal to 1, well, it is just immediate from part A, right? We already proved in part A this subset thing. And so, well, we've got, A is a subset of omega, right? Any event is a subset of omega. Well, from part A, we get that therefore the probability of A must be less than or equal to the probability of omega. And we know that the probability of omega is equal to 1 by what was the second axiom. And so there you have it, right? This is a chain of an inequality and an equation. So this proves what we wanted to prove, right? It shows that the probability of A is less than or equal to 1. Okay, let's move on to the last one. Again, we're going to assume that A is a subset of B. We're trying to prove the excision formula. And we've already seen that under this condition, the probability of B is equal to probability of A plus probability of B minus A. And then all we have to do is subtract A to the other side, right? When we subtract A to the other side, we get this, and that's the proof complete. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.